Hello everyone, welcome to part 2 of the unsupervised learning lecture. So today's lecture is going to continue on previous lecture where we were looking into autoencoders and variational autoencoders. So today we're going to look into conditioning these autoencoders. So how do we make sure that we can condition on certain variables of interest, for example the age of the patient or the disease that the patient might have, when we're trying to generate or encode data. We're also going to look into ways for us to disentangle or factor different components of the data using unsupervised learning techniques. We're going to look very briefly into generative adversarial networks and Watersheim GANs and ways to penalize them using these. And very last, we're going to look into vector quantized models, which are ways to do autoencoding or achieve a form of unsupervised learning with a much more compact quantized representation. So in this specific example that you have here below, this paper from Week7 2018, conditional variational autoencoders do exactly what you would expect them to do. So they are variational autoencoder, exactly the same diagram as we had in the previous lecture. But at the current moment, there is one thing that changes, which is the fact that there is a conditioning variable which is concatenated to the sample latent vector Z when you are about to decode. So this is what happens in this area here. You see that here, for example, C is a conditioning variable. Let's say, again, the age of a patient or a disease status of a patient. And we are concatenating this variable to the sampled latent representation Z, which means the decoder now has two components of information. It has the sampled latent representation, and it has this extra variable here that allows us to reconstruct an input where this variable here is influencing the output that is being reconstructed. You would then be able to argue that the sample latent vector itself, if given an image with a specific conditioning value C, the sample latent vector should contain the same information. So you could argue that the information that is here, that is containing C, because that information is also contained on the image itself, on the image X, this would be concatenated with C, which will be non-ideal. So what happens is that C is also provided at this stage. So it's also provided prior to the variational component of the network, which means in order for the network to create a compact Gaussian-like representation here, using these means and variances, it learns to regress out the value of C out of whatever is modeling here, because the same value of C is going to be added later on and concatenated to the vector, the sample latent vector, later on into the network. So if any information about C was to be preserved within the mu and sigma and subsequently on Z, this would actually make the network non-optimal from the information perspective point of view. So if the only information that is available in the probabilistic variational component of the network and in the sample latent vector is information that is not present in C, then this becomes optimal from the point of view of this bottleneck. Another method that is quite interesting when it comes to ways to do variational autoencoder is to think about the weights that exist between the KL divergence, which we've seen in the previous lecture, that basically forces the latent space distribution to be Gaussian distributed, which is what's being optimized here when you have this KL. And this is being optimized obviously at the same time that you have the fitting function, the thing that is evaluating the quality of the reconstruction. So the KL divergence itself is a measure of distance between two probability distributions. And if we now introduce this weighting here, this beta weighting here, we're basically increasing the weight of this Gaussian prior. So this forms a Gaussian prior. It tries to enforce this variable here, distribution here, to be Gaussian distributed. And by increasing the value of beta, what we're basically doing is we're making the KL divergence have a higher weight in terms of the total loss of the network, which means it's going to force even more the code distribution to be Gaussian-like. The other interesting thing is that the prior distribution here is a prior distribution where the code is not only Gaussian distributed, but normally is a Gaussian distributed with a diagonal covariance matrix, which means that the Gaussian is axis aligned, let's say, in the space of Z. And because the Gaussian is axis aligned in the space of Z, In order for this distribution here, this Q of Z given X, to approximate this Gaussian distribution, this prior distribution, it will force the distribution of the latent representation to also be a axis-aligned Gaussian. So increasing the value of beta forces zero correlation to exist between the different components of Z, which again promotes disentangling. So beta VAE methods are nothing more than introducing a beta scaling factor on the KL divergence. And depending on how high the beta factor is, we are forcing more and more information to be disentangled. Obviously, because there is all this information that can never be disentangled, the quality of the reconstruction will become worse when we make the beta too large. So there is a balance to be had between how do we disentangle the data with the KL component and how accurate is the reconstruction with the fidelity term. So this slide here presents an excellent demonstration of exactly what different values of beta do when you're trying to reconstruct an image. So in the very top row, what we have here is we have the input data that we're providing to our variational autoencoder. So here you basically have a sphere, a blurry sphere, or circle in this case, that is located at different points of the space of this image. So sometimes it's closer to the top, sometimes it's closer to the bottom, sometimes it's further to the left, sometimes it's further to the right. So when we are doing variational autoencoding of this information, if you think about it, the information that exists here is actually quite simple. The circle, or the blurry circle, is always of the same size. The amount of blurriness is always the same. The only difference between these circles is the fact that the position of the circles is different. So if you were to do variational autoencoding of this image here that you have at the top, this is the image that you would have with a reconstruction if your beta is equal to 1, which is a standard VAE. You see, reconstruction is pretty accurate, is able to localize to tell you where the blob is, and is able to reconstruct the image very easily because the image is quite simple. There's not much content beyond the blob in a specific location. However, if you're not going to look into specific components of the code distribution, so of the space of Z, and if you're going to change, for example, what the reconstruction will look like, if you were to change the first component or the second component or the third component of the latent space Z, what you see is changing the first component would make the blurry circle move from the central location to the top left. When you're changing the second element, it goes from roughly the center to the bottom. The third element is moving the circle to the right. The fourth element is keeping it in the center until the very end, where it suddenly goes down. And the fifth and sixth elements are really meaningless. They just keep the circle in the same place, so nothing really changes. So you see here that the gradient, or the directionality of where these things are in space when you change the value, is not really axis aligned, and is basically using more dimensions to encode the position than it should, right? Because everything should be either left or right, up and down, and if you have those two, it should be enough for you to reconstruct any image. And clearly here, there's 4 latent representation Zs, which are being used to be able to reconstruct the image. If you significantly increase the value of beta, for example, in this case to 150, you see in the second row that the reconstruction is much poorer. So the brightness of the spot is lower, and the exact location is not precise. For example, here you see, here at the end, you see that this is not as close to the top as this one is. And this one here is also pretty obvious, where this one is pretty much touching the left side of the image, while this one here is a little bit further away. So the reconstruction is not as good as it was in the previous one, where it was pretty much perfect. However, if you now look into the different channels, you basically see this. You see that the first channel encodes literally down and up, all the way from one end to another end. The second channel encodes right to left, and again, if you look at the gradients, they are now perfectly well aligned. The other channels do not encode any information at all, and have a variance which is very large, which means that they're pretty much not contributing any information to the overall system. So we have now created a system by increasing the value of eta that promotes disentangling of the factors that influence the generation of the data that you see at the very top of the original image, even though it does penalize slightly the reconstructions. So if you're interested about introspecting what are the modes of variation in your data, and not necessarily to get the best possible images that you can in terms of reconstruction, you should really look into beta VAEs or any of the models that have superseded it since then. Factor VAEs are actually quite similar to beta VAEs in the sense that what they're trying to achieve is to disentangle representations. But here, rather than penalizing the KL divergence, which is what we were seeing in the previous example, so you see here in the KL divergence term, there is no beta component. We're just using the KL divergence by itself. And the reason for it is because they realize that penalizing the KL divergence too much, it impedes the quality of the reconstructions. So what we want when we want disentangling is that we want the different dimensions of Z to be non-correlated with each other. So we want them to be orthogonal, we want them to be as disentangled as possible, so we want the correlation to be minimal. And this is what they did by adding this extra term. So here Q of Z is the distribution of the code itself, the probability distribution of the code, and Q tilde of Z is basically a distribution over assuming that the different components of Z are independent from each other. So if all the components of Z are independent from each other, this factorizes into basically a product of the probabilities of the different components independently. And you now calculate the KL divergence between this probability and the actual probability that you observe. So the one that assumes that things are factorized and the one that does not assume that that's the case. And obviously you want to minimize the KL divergence between this because this is going to promote the fact that Q of Z should be factorized as much as possible. So this is another way for you to enforce the orthogonality of the code representation Z and the fact that there is very little or no correlation between the different components of that vector. Okay, so now that we've seen quite a few things about variational autoencoders, one part that I think is quite important to understand is how can variational autoencoders be used to generate new random samples? So one important factor to see in variational autoencoder type models is that the code distribution, the latent space Z, is Gaussian distributed, which means if we feed into the latent space Z a series of numbers, randomly generated numbers, which are also Gaussian distributed, the model is going to map those numbers back into the space of an image. So you can now ask, how do you actually get Gaussian distributions from your computers so that you can feed them into these models? One way to do so, and again, there's a million different ways to do this in different languages. In many languages, you actually have ways to generate Gaussian variables by themselves. But the way that actually works in many of the computers is that you have a random number generator, which is uniform. So it's something that is generating a value between 0 and 1. Any number between 0 and 1 is going to be valid. So it's generating what we're seeing here in the blue line. So this part here, it's generating a number between 0 and 1. Then what it does is it takes this number between 0 and 1 and it puts it through the cumulative distribution function of a Gaussian distributed with mean 0 and standard deviation of 1. So if you now feed a value of y, so you see here in the y-axis, if you get a random value from this uniform distribution here, let's say you get the value, when you're sampling from this distribution, this uniform distribution, you get the value of 0.2. You take this value of 0.2, you go to this distribution, you go there to the location 0.2, and that is going to give us a value of the Gaussian distribution, which is going to be, let's say, 0.8. So we have now transformed a value, which was between 0 and 1, into a value which is between -5 and 5, which is roughly the support of a Gaussian function. I mean, the Gaussian function has infinite support, but this is the support where you have values of probability which are significantly different from 0. But you see that you've managed to map a value that was uniform in the space of 0, 1 to a value that will then be Gaussian distributed in the space of x in this axis here. You also see that, for example, for locations where the Gaussian samples will be -5 or -4, these will be very unlikely settings. The value of the uniform distribution would have to be really, really close to 0. So you can immediately see that the likelihood of you picking up a -4, a -3, or a -5 in this Gaussian distribution will require the generated uniform sample to be very, very close to 0. So the likelihood is lower. But for example, for you to generate a value between, let's say, -0.5 and 0.5, you actually have a pretty big area of numbers, roughly between, let's say, 0.3 and maybe 0.7. So this full range of uniform values will give you a Gaussian distributed value between -0.5 and +0.5 in the other domain. So why am I talking about this? I think it's important to understand that in a generative network or in a VAE or autoencoder, what we're doing is we start from we feed this network a random variable. So this random variable is literally just a vector of random numbers according to some distribution that the model assumes. For example, in the variational autoencoder model, the encoder projects the image into a Gaussian distributed latent space, and then the decoder takes the latent space and brings the latent space back into the domain of an image. So if you now think only about the decoder part of a network, so if the network did not have an encoder, what you basically have is you have this generative system where if you feed a Gaussian value into the decoder, in this case called generative network, the decoder is going to transform this vector into a different vector, which when you reshape it is going to generate this image here, which is going to look like a dog or whatever this image is. So the idea here is that there is two components. There is one component of a generative model, which is to sample values. And when you sample these values, you feed them through a generative network and you generate the generated distribution, which is here in orange. So you generate some points in some high-dimensional space. So in this case, this is a two-dimensional point where in x and y you have the first and the second element of that two-dimensional vector. But obviously, if you're looking into an image, if the image is, let's say, a 16 by 16 image, then the image would have 256 different dimensions, which means you will be looking at a 256 dimensional point that is being generated. But the point that I'm trying to make here is that if you sample a random value and you give it to a generative network, you're going to generate a point in some distribution space, and you now have some points that you might have observed already of real images or real vectors, right? A real true distribution. So if you imagine the blue points here, or the blue circles, being the dimension or the location where these points would sit in a high-dimensional space for real images, so images that have been observed. If the generative model generates points that are in the orange location, you see that there is a distribution mismatch. So the points in orange and the points in blue do not overlap that much. And because they do not overlap that much, there is a discrepancy between these two distributions, and what you can do is you can backpropagate through your network and basically tell your generative network that whatever point is generated, so the way it's converting these orange circles on the left into this orange circle distribution on the right is not good enough, and there is a change that needs to happen in this generative process to make sure that distributions match with each other. So when we are trying to match the different distributions with each other, what you end up is with points in some high-dimensional space. In order to simplify the explanation, let's turn that into a one-dimensional problem. So you're just trying to generate a single-dimensional value, not an image, but just a single scalar value. If the ground truth distribution is the blue curve, or the blue Gaussian distribution, and the generated distribution is the orange one, it becomes pretty easy to see that there is a mismatch between the two distributions, and that in order to bring the two distributions together, we need to bring the orange distribution closer to a mean of -1, and the variance needs to go from 1 to 2. And we see that at each one of the steps, as the orange curve is approximating the blue one, the distance between those two curves is getting smaller and smaller and smaller. And it gets to a point where the two distributions are overlapping. And when they overlap, then they are indistinguishable. So everything that I said in this specific slide relies on some idea of measuring distances between these two distributions. And also it relies on the idea of optimizing the parameters that generate these distributions so that the two distributions can match better and better and better at each one of the steps. What you see here is that there are many ways to distinguish or bring these two distributions together. But one way to do so is to use discriminators. So if you were to train a classifier in this one-dimensional space that was trying to predict if a point belongs to the blue curve or the orange curve, depending on its x value, for the first figure that you have here, for example, you would say that any value that is on the left of this crossing point is more likely to be part of the blue distribution, while any value that is on the right of this point is more likely to belong to the orange distribution. This is what we're seeing here. So this decision function here in blue is saying that this is the location where a point would go from belonging to the dotted black distribution and started becoming part of the dense green distribution. So this decision function here can be used as a metric to be able to distinguish between these two distributions. If you start bringing the two distributions closer and closer together, the next step is probably going to look something like this. And we see that the decision function now becomes much harder. We know on this side, we're definitely on the field of the dotted black distribution because that's the one that is highest. But when we go slightly further to the right, we get to the point that it becomes actually quite hard to know which one is the highest, which distribution has the highest probability. Is it the green or is it the black? If the two distributions are perfectly aligned with each other, then the best the discriminator can do is to give you an answer where the probability to be part of green or blue or black is exactly equal to 0.5 all the time for every single point in that distribution. This means that the discriminator fails to separate the two distributions because for every single location x, the likelihood of being, or the probability of being part of the dotted blue or dotted black distribution and green distribution is the same everywhere, which means they cannot be distinguished anymore. So a classifier can be used as a metric. So if the classifier can classify and can separate two distributions, it means that they're far apart. And when it comes to the point where the classifier cannot separate the two distributions anymore, then we know that the classifier has failed to do so, and because of that, that probably means that the two distributions are now perfectly aligned because there is nothing in the distributions themselves that allows the model to be able to distinguish between them. Obviously, the same idea can be applied to higher dimensional vectors than one-dimensional vectors, and this is exactly what GANs are. So in a generative adversarial network type setting, primarily for generating new images, what happens is that you have a latent vector z, which is being sampled from some distribution which is known, let's say a 0 to 1 distribution or a Gaussian distribution of sorts. Random samples are being fed into a generative network, so a network that the role is to map random values into the space of another high-dimensional vector, for example, an image. So each one of these points here is going to represent an image, and the points that are generated here are the blue points. The role of the discriminator is to then go and find the best separating hyperplane between the red points and the blue points, where the red points are real images. So the points in blue are fully synthetic. The ones on the very left are generated by a Gaussian sampler or uniform sampler. They're given to a network, and the network is generated pseudo-synthetic images. So all these points here in blue are synthetic samples. They do not exist in reality. And what we would like is to change the parameters of this generative network so that the blue points overlap with the red points as much as possible. The way we do this is by training a discriminative network that tries to find a separating hyperplane between red and blue. And if we add this discriminative network, obviously, if we're training this discriminative network to maximize the ability to discriminate between the two, what we can do is when we backpropagate through the network, we can basically tell the generator to optimize for the inverse of what the discriminator is normally going to optimize for. So the discriminator is going to try to find the best hyperplane, but we want to optimize the generator to minimize the discrepancy of the discriminator itself. So we want to optimize for the negative part of the gradient, or the negative version of the gradient of the discriminator. So what it normally happens is that when you're backpropagating through the network and you're going from the discriminator to the generator, you reverse the sign of the gradient, which means you're now training the generative network and changing the parameters of the generative network so that you are making the discriminator work less well, which means you're forcing the samples to be more confused from the point of view of the discriminator, which means that will move the blue samples to be closer and closer to the orange samples here. At each one of the steps, every time a gradient flows back, the points are going to move slightly slower, slightly closer to each other. And what you see here is that the decision boundary becomes a lot fuzzier. For example, in this section there, the orange and the blue points are starting to overlap, and the decision function says anything above this point is blue, anything below this point is orange. There's already a few points here that are misclassified, so the accuracy of the discriminator is not 100% anymore, is probably in the 60s or 70s or 80s. These points over there, they're still very well classified. So the next step will force the network to push these points further down so that this classification is performing worse. If you keep doing this over and over again, it will get to a point where the orange and the blue points are exactly the same, and the discriminator will not be able to separate them because there is no simple or relatively simplistic hyperplane that is able to discriminate between these two distributions. That means we have now brought the distributions of the real data and of the synthetic data closer to each other, and by doing so, we have now tricked the discriminator. The interesting thing about generative adversarial networks is that it is a game of cat and mouse. On one side, you have the discriminator trying to make sure that it can better separate between the truth and the synthetic domains, or the samples coming from the real world, from real images, and the samples coming from the generator. It's trying to maximize that ability to discriminate between the two. But at the same time, we're also telling the generator itself to generate better and better images that are able to better trick the discriminator to make mistakes. So if you think about it, this is, I was giving the example of the cat and mouse game, but if you think about another example, for example, if you have someone trying to forge banknotes, and you have the police trying to detect how these forgers look like, this game is going to continue forever until the point where the forgers cannot forge notes that can trick the policeman anymore, or until the point where the forgers are so good at generating banknotes that they are indistinguishable from the true notes, which means that they will never be able to find which ones are the fake, which ones are the real ones. The algorithm of the generative adversarial networks is quite simple, actually. So what you do is, for the number of training iterations, you do a series of steps. First part, you optimize for the discriminator by ascending through the stochastic gradient descent part. So you are basically optimizing the discriminator to be able to maximize this probability here, this log likelihood of the discriminator performing what it's supposed to do, and also to try to make sure that samples that's generated by the model are also part of the negative class. So you're training the discriminator to do a better job at discriminating between X and G of Z being the synthetic data. This is for the discriminator training, and you do it for K steps. After K number of steps, the discriminator has converged to some reasonable number, And what you would then do is you would sample a mini batch of noise samples Z, and then after you have that mini batch of sample noises Z, you feed them through the generator, and then you put them through the discriminator. But now what you're trying to do is you're trying to do the opposite. So you're descending the stochastic gradient descent. So you're trying to make sure that the generator is being optimized to be able to better trick the discriminator. If you now iterate between these two, every time that you're doing this series of steps here, you're improving the discriminator ability to discriminate between the two distributions of images. While in this other step here, you're making the generator better by forcing the generator to optimize its parameters to be able to better trick the discriminator that has been trained in the previous step. And if you iterate between these two, you would expect to reach some sort of equilibrium, which in this case is called Nash equilibrium, where the two losses are going to be balanced each other. So they are never minimized because there is no minima that minimize the two at the same time, because you're both ascending and descending a loss function which is very similar across the two networks. The problems with GANs, as I was describing before, is that they're trying to reach this Nash equilibrium. So if you think about it, if you have two functions here, let's not even think about very complex functions like GANs. Let's just think about two very, very, very simplistic functions. So if you want to update the function x to minimize the function x times y without having access to the function y, what is happening is what you're seeing here, right? So you have xy, which is this black line here, right? At this point, xy has this value here. So if you want to update x, which is the one in red, to be able to make sure that xy is minimized, x is starting to go down. And by x going down is going to mean that xy is also going to start going down. So xy follows x because you're multiplying x and y, right? But if the task for y is to minimize the negative of x times y, then when xy starts going down, because you want to make it higher, so you want to bring xy to make it higher, actually, you want to minimize minus xy, then you're going to make y go higher and higher and higher, right? So now y starts going up, and when y starts going up, then the x times y keeps going down and it suddenly crosses the zero line. When it crosses the zero line, then x starts realizing that he needs to turn around and start going up. But when it does that, in order for y to minimize the minus xy, y also starts going down. And basically they have a contra-symbiotic relationship, actually a destructive relationship. That means that the functions x and y, if optimized to minimize and to maximize xy, what is going to happen is that the functions themselves are going to become larger and larger and larger, and the function minus xy, or the function xy, is also going to start having a higher and higher and higher amplitude. And this is just the consequence of the oscillatory process of trying to minimize one thing while the other function is trying to minimize the opposite. And Nash equilibrium is what happens when these two things actually converge in a non-destructive way. If you were to play with how you optimize x and how do you optimize y at the same time, by controlling the number of steps and the training regime, and for example, the step size of each one of these different gradient descents that we're applying to these different functions, then we might end up in a very different solution and the Nash equilibrium might actually be reached. GANs have several issues. The first part is the fact that images are very high-dimensional objects. And when you are in a very high-dimensional space, it's very likely that there's going to be a hyperplane or a separating hyperplane that will generate and separate real and synthetic images. The other issue is the fact that because this space is so high-dimensional, if we need to have a lot of data to be able to have overlap and support between the two distributions. If the two distributions do not have enough overlap and support, then the discriminator is going to be perfect all of the time and the network will never be able to train. The other part that happens is that the gradients of the discriminator, they vanish very, very quickly. So for example, if you calculate the gradients from the point of view of the generator given by the discriminator, so the ones that are actually optimizing the generator parameters in order to be able to trick the discriminator, what happens here is after 1 epoch or 10 epochs or 25 epochs of training, the amount of gradients that you're going to see here are going to go down very, very quickly, and they will approximate negligible values very, very quickly. That means that the generator can learn to trick the discriminator very quickly, but obviously tricking the discriminator as it currently stands is not necessarily what it should be doing, because the generator itself can learn how to trick the discriminator not in a way that is realistic, but just in a way that tricks the discriminator. If we now train the discriminator again, the discriminator will very easily recover, and now the generator might be doing the completely wrong thing because he tried to trick the discriminator, but again, not by generating realistic patterns or realistic images, but just by generating a pattern that tricks the discriminator. So the only way for these two models to converge is for the generator to actually generate images that look realistic, because that's the only setting where the discriminator will not be able to discriminate between images any longer. The last issue that also exists with GANs is something that is called mode collapse. So mode collapse happens because in a GAN setting, we're trying to figure out if the generated samples belong or do not belong to a distribution. So the simple example of what mode collapse is for example, the situation where a generative network is generating, for example, pictures of cats, dogs, and zebras. Or if you want in a medical setting, let's say brains, livers, and hearts. If you have a generator trying to generate different images with brains, livers, and hearts, if the generator network only learns to generate brains, for example, it never learns how to generate livers and hearts, the discriminator cannot say that just because the generative network is generating brains, that those brains are fake. The brains might look very, very realistic. However, the generative network has a much easier task because it now only needs to generate one type of thing rather than the three types, the three organ types. So the generative network has collapsed onto a single mode, in this case the brain images, and he has ignored the fact that the liver and cardiac images are not being generated. And from the point of view of the discriminator knows that if the generator generates a brain image is more likely to be fake, even though the real data set also contains brain images. But it knows that if the generator generates, for example, a liver or a heart, those are going to be very unlikely because it's not something that the generator does very often. You could also argue that the discriminator could basically just say, okay, so if the generator is generating a brain, then I'm just going to say that that's a fake one to force the generator to generate something else. But what happens is what you're seeing here at the very bottom, where the distribution might have converged to a specific point. So this is the target distribution. The distribution might have converged to one of these points, for example, this one here. And when the discriminator realizes that the generator can only generate points that belong to that specific location, the generator just flips and moves to the next point. For example, it starts moving to this one. So now the discriminator has learned that if points are being generated along this point, these are likely to be fake. Because the generator learned that the discriminator figured that out, it starts generating these other points here now. Only these points, and stop generating these other ones. Which means the discriminator now needs to adapt and say, actually, we're now looking to the next point. Obviously, if you use steps down the line, the discriminator figures out that now the generator is only generating these points here, and it becomes optimal for those. And the generator now flips and starts generating the next set of points. You see here, we're now moving to a different mode of the distribution. So there is this mode collapse is not only the issue of not generating the variability that you'd expect in a training set because you're focusing on one specific mode of the distribution, but it's also the problem that even if the discriminator realizes that that's the case, a distribution with many modes can cause the generator to keep flipping between modes, and you might end up with a generator that flips between many different modes. There are ways to fix this, and there are ways to make sure that distribution needs to be matched between the target and the source, but those are more complicated GANs than the ones that were presented here. So GANs in a medical setting have been used quite extensively, and the reason that they've been used quite extensively is because generative adversarial networks can generate synthetic data that looks like it's real, which means if we have a very good generative model of imaging data, we could then create, in theory, an infinite amount of data. You could argue that whatever the GAN model can learn is also reliant on the real images that are fed to the GAN model. But depending on the construction of the generative model, we can actually have a generative model being able to generate images with more variability than the ones that are used to train it, which means it can still provide a valuable source of heterogeneity when it comes to data that can be used to train a model further downstream. And the reason for it is, for example, if you were to train a GAN model to generate, for example, in this case, some retinal images, and if you were to train then a discriminator to distinguish between real and generated images, you'll end up with something that can generate images that look like retinas and that look like eyes. The other interesting thing is if you actually look at the discriminator, in this case the discriminator that was used to discriminate between real and synthetic images, and if you were to look at the features at the very last layer of the discriminator, so the features just before you actually discriminate between real and fake, and if you were to do a nonlinear dimensionality reduction of that feature distribution using something like TSNE, what it happens is the two biggest modes of variation, in this case these two TSNE distributions, end up separating quite well normal and anomalous images, which means the ability to discriminate images actually creates a feature representation which is somehow biologically informative, and we can now use this representation, which was used purely to generate new images, as a way to be able to classify images into normal and anomalous. This has been applied to really many different areas. For example, here you have a generative adversarial network, in this case a conditional generative adversarial network, that is fed an image as a primer and is trying to generate a synthetic version of another modality. So these models are still GANs. Actually, they probably shouldn't be called GANs, even though that's what they are normally called in the literature. They are methods that use adversarial losses in order to match the distributions between the synthetic image and the true images of the synthetic target. But these adversarial methodologies basically take an image as an input, they pass it through a network to generate an image of another modality, and then they use a discriminator to be able to show or to be able to make sure that the generated image can confuse the discriminator that has been trained to distinguish between fakes and real images of this target distribution. This allows you to, for example, match and map MRI images to CT images and CT images to MRI images, which means you can now translate data sets from one to the other. This slide here is showing another example where these generative adversarial networks can be used to generate more than one output at the same time in a way that is consistent. So on the left you have some fundus imaging and the associated angiographic image. They've been generated in a joint manner, which means not only the generative model has generated these two at the same time and understands how fundus images relate to the angiographic data, but he has been able to generate these two different modalities in a way that is biologically realistic and compatible with each other. You also have on the right a generative model of 4 different brain MRI contrasts at the same time. In this case, T2, contrast T1, flare, and pre-contrast T1. And you see that is able to generate the 4 modalities at the same time in 2 dimensions. You also have other interesting applications. So this is a video from a company in London called Kieran Medical. It's a paper that was published by Kieran and some colleagues of mine at Imperial College. And this paper here is demonstrating that you can generate some very high resolution and very realistic synthetic images of breast mammography data. What you're seeing here is the latent space that I was talking about, is random Gaussian latent space. If you travel in that space, so if you have a trajectory in that latent representation, so just passing through a series of points, connecting them with lines or something like this, you can then decode the images. So you can generate the images for each one of the locations of that code space, which means you're traveling in the space of different breasts, and you can, by decoding each one of the times, you can create these movies. So these movies are not movies of the breasts themselves changing, or you're not slicing through them. They're just images of breasts, of different breasts that can be generated by the generative adversarial network itself. There are many things that can be improved in generative adversarial networks, many of them which have happened recently in recent papers, some of them which are part of the to-do list of many researchers out there. But for example, making sure that the features themselves of the images can match, something that is called, for example, perceptive losses are now being used as ways to stabilize GANs. You can also make sure that the discriminator itself can look at multiple data examples in combination as part of a mini batch. You can, for example, use historical averaging to make sure that the parameters do not change too much. For example, if one of the batches of your model contributes too much in terms of gradient and enhance the full model. You can do label smoothing, where you are allowing for some of the predictions of the model and the data, in this case the discriminator behavior, to be less strict by situations where the discriminator might make a very strong prediction, saying these data, for example, is absolutely realistic ground truth data, but in reality it's false. So if a discriminator makes such a mistake because of the terms, the cross-entropy terms that are used to optimize the discriminators, it can cause a logarithm of 0 to happen, which is very detrimental to the model, as you can imagine. So by doing label smoothing, you can make sure that the discriminator is better well behaved and can make predictions that are a little bit more aggressive without being overly penalized from the point of view of the cross-entropy loss. You can also use other things like virtual batch normalization and adding noise to the discriminator to make sure that you can stabilize the training. But the reasoning that all of these things are necessary is because GANs are actually super complicated to train and very unstable, and also incredibly hard to reproduce. But when they work really well, and they can generate very impressive images. Another way to match distributions, in this case the distribution of P in orange at the top and the distribution of Q in green at the bottom, there's many ways to do so. For example, the KL divergence is one way, and using discriminators is another way. There is many other ways to do this, but one way that has been significantly explored in the domain of generative adversarial networks is something called the Watersine loss, or the Watersine distance. So if you're trying to match these two distributions, you can do so by moving probability between one bin, for example P1, P2, P3, and P4, and by moving these probabilities between bins, we are then matching the two distributions. So for example, if you compare orange and green on the first step, on step 0, you see that the value in P1 is much larger on the orange distribution, on the distribution of P, than it is on the distribution of Q. Because of that, what the model can do is to say, okay, in the next step, what I'm going to do is I'm going to move some of the distribution from this part here, because I have 2 units more than I have on this one, and I'm going to move it to my class next to it. You see that these 2 units here have now moved to the next line. So this is step 1. Step 1, you're moving from right to left. You're just moving this probability density to the right. If you now compare these two distributions, the same thing happens. There's 2 units here and 2 units there. So this orange distribution has 2 units more than it should, which means it needs to move these 2 units again to the right. That gives you the third iteration. You see, in the third iteration, we now have 1, 2, 3, and 4 units in bin 1, 2, 3, and 4. But in the target distribution, what we have now is we have Q1, Q2, Q3, Q4. You have 1, 2, 4, 3, which means that the third bin has one more element than the third bin here at the top, while the fourth bin here has one less element than the one over there. So what we can do next for the next step is to basically bring one of these elements from the previous the previous step and moving it forward. So if we take that distribution there, that element there, and we move it to the next element, we are going to make the last element now have 4 components, and now the 2 distributions are perfectly matching with each other. So we moved a little bit of the density from Q3 to Q4, and by doing this, the 2 distributions now match. You see, you have 1, 2, 3, 4, and here you have 1, 2, 3, 4. They are exactly the same distribution. So this process that you've seen here is something that is called the earth mover's distance. Is the idea that we're going to move probability as if it was dirt, and what is the minimal amount of energy or the minimal amount of movement that you could do to move certain piles of dirt, or in this case certain probabilities, from a specific topological mountain set, if you're thinking about dirt again, or in this case a probability distribution, to another probability distribution. So why is the earth mover's distance better than the KL divergence, at least for the purpose that we have here? The reason for it is, for example, imagine that you have 2 probability distributions which are not very well behaved. P and Q in this case. You see that P and Q have the full probability, in this case the full probability mass of 1 at one specific location. So P has the full probability at 0, while Q has the full probability at 0.5. Which means if you were to calculate the KL divergence between these 2, you would basically be having a loss that will look like this. So if you were to change the position of the 2, the loss would be pretty much 0.7 throughout the full spectrum, and only when it gets to a very precise location, the loss is going to be 0, and then it's going to go back to 0.7. It's going to continuously be at 0.7 throughout. So you see that depending on the position of these 2 distributions, the loss function doesn't really move much for any if you try to get them slightly closer to each other. For example, if the red distribution moves to 0.2 or even 0.4, the KL divergence doesn't really change. It only changes when there's overlap between the 2 distributions. And as we've seen before, the space of images is very sparse because it's very high dimensional. So there tends to be very small overlap between images, which is why KL divergence doesn't tend to work very well. However, the earth mover's distance, the amount of effort made to be able to move distribution to this other distribution, is actually a continuous function that is changing in space. So the closer they are, the lower the earth mover's distance is. And because this function here has a gradient, it has a slope, we can actually optimize for it. While for the KL divergence, we cannot really optimize for the KL divergence itself. So now that we've seen these generative adversarial networks, the interesting thing about these generative adversarial networks is that the most interesting part, at least for me personally, about these generative adversarial networks is the AN part of the name, is the adversary. Is the idea of using a discriminator to be able to make sure that the network can or cannot distinguish between images, feature sets, or anything like that. So is the idea of using a discriminator as a way to make sure that the network can or cannot distinguish between certain types of things. You can now start using the same concept, the adversarial concept, in other settings. For example, if you have a variational autoencoder, when we're taking an image, projecting it to the space of Z, and then getting an X tilde back. So we're putting it through an encoder and a decoder. That part is what you would normally have in an autoencoder or variational autoencoder. If you now have what is called variational autoencoder GAN, what you're actually doing is you're just adding the discriminator at the end. When you're taking X and you're feeding X to the discriminator, so this is what you're seeing here, we're taking X here and we're feeding X to the discriminator again, and we want the discriminator to be able to find differences between X and X tilde. You could argue that this is very similar to what we had before when we were just feeding random variables to Z and then decoding. So you don't really need an encoder. But the interesting thing here is that these samples here are paired. So X tilde is a reconstructed image, but X is the original input image that we gave to the encoder. which means the discriminator here is going to be given two images, and these two images are very similar to each other, and whatever is left of the difference between them is things that the encoder and the decoder cannot model. So the discriminator here is not just figuring out if the image is real or generated from the point of view of the quality of the image that is generated, but is actually trying to figure out what are the characteristics that cannot be modeled by the encoder and decoder, because those are the features that is going to use to distinguish between x tilde and x. Which means that when you backpropagate through this and you invert the gradients, you're maximizing or optimizing the encoder and the decoder to be able to trick this discriminator. The encoder and decoder will be forced to better reconstruct the things that are allowing the discriminator to be able to discriminate between real and synthetic. This has been used in the medical imaging setting now in a couple of papers. For example, here is a paper where they were taking an image here, for example, in this case, this real image, putting it through an encoder. The encoder was getting it some code space Z. Then this code space Z was being decoded or being generated back to be able to have an X reconstructed. You would also do another step where you'll be able to generate a random vector Z, which is going to generate this reconstructed random image. And we can now give this triplet of images to a discriminator. So a real image, the reconstructed version of the real image, and a completely random sample, which was generated by randomly sampling from this Gaussian vector here, from this latent vector here. And for the discriminator to be able to discriminate between these three, it needs to understand differences between real and reconstructed images of the same subject, but also be able to generate random images that are of good quality enough from whatever distribution we're feeding into this Z of R. The other thing that we can do is to make sure that the code distribution of the encoded real, so ZE, and the code distribution of the random generated image, which for example could be a Gaussian, when fed into the discriminator cannot be distinguished. So this, if we sample always here ZR as a Gaussian distribution, but we don't have any prior over ZE, this discriminator here can actually enforce a prior, because if ZR is Gaussian distributed, but ZE is not, it's going to be very easy for this code discriminator to discriminate between ZE and ZR. So it will force ZE to have the same distribution as ZR, so that the samples are indistinguishable from each other from the point of view of this code discriminator. So this model here is really interesting because it does two things, or actually several things at the same time. It can reconstruct via the encoder decoder. It can force ZE to have a certain distribution by using the code discriminator versus this random sample ZR. And the same random sample ZR is generated these random images, which means the discriminator needs to understand both differences between real and reconstructed images of the same subject, but also random samples generated by the model, and all of those need to be properly classified as real or fake. There's several papers that have been published in this domain, and here you have some examples of different models trying to generate some three-dimensional images. Unfortunately, because of hardware limitations and the type of techniques that are being used, most of the papers published so far are either in 2D or very low resolution 3D imaging data. And in the 3D imaging domain, because the sizes of the models become very large very quickly, the quality of the reconstructed samples is not great. It's getting there, but it's not great. For example, here what you see is the results of the 3D WGAN, the VAE GAN, the 3D alpha GAN, and this proposed method that was proposed in this paper here. And you see that the proposed method and that is generating probably the most realistic images. The VAE GAN, even though it does have the GAN component, the adversarial component, is still generating images that are really blurry, as you'd expect from a lot of the autoencoder type models. While the alpha GAN is generating images that are quite speckly, as is kind of perceived from the original paper. You clearly see, if you read the original alpha GAN paper, that this is the behavior that you would expect for most of these methods. The other interesting thing about GANs is that everyone is trying to glue different components together to make probably the longest and more complicated and convoluted names that you could possibly imagine. So here is a figure from a paper where they propose the conditional VAE GAN. So the conditional VAE GAN is kind of everything in the kitchen sink approach. So you have the VAE GAN at the top, which takes an image, puts it through an encoder, gets a latent space, and puts it through a generator or a decoder, and then gets X prime. A GAN, which does not have the encoder, it only has the generator and the discriminator next to each other. The VAE GAN, which tries to bring these two together, so you see you go from X encoder latent space, decoder X prime, discriminator Y. So this is where you're trying to discriminate if the image is of true or false. The conditional variational autoencoder, which is one that we saw at the beginning of today's lecture, it feeds the conditioning value in the encoder and in the decoder, meaning that the code space only contains information that is not present in this conditioning variable. You can also do a condition GAN, and there's papers that do this, where you feed the conditioning element into G so that you can generate X prime, and then you want the discriminator to also have access to the same information. So you want the discriminator to be able to distinguish between X and Y by being fed this conditioning variable itself. So there's all of these methods here can then be combined again further in different ways. For example, in these other two methods, the CVAE GAN and this PPGN GAN, all of these different methods basically use the same kind of setting where you're trying to have a discriminator discriminating between real and fake images, but you also want to have a classifier that tries to take the generated image and predict what the covariate of interest would be. What does that mean? Imagine that you have only this first part here, only the VAE GAN. You have an image being fed into an encoder, and you're feeding also a covariate, let's say the disease status of the subject. That means the latent representation, because it wants to be compact, will not have any content from this covariate here. So the Z is going to represent a subject phenotype, but regress out information, for example, about the subject's disease status. The subject disease status is added again to the generator, which means the generator can now reconstruct X prime in a way that contains that disease, and X prime needs to be similar to X, and it needs to fool the discriminator down here. But if X prime contains the information of C, so in this case the disease status, then if we give X prime into a classifier, the classifier should be able to classify the right status. So you should be able to say that X prime indeed is a subject with a specific disease type. So this extra classifier here forces X prime to contain information about C, and this information about C is fetched from this other C that is given to the generator. And again, because Z wants to be compact, then it forces the C here fed into the encoder to remove the information. So you now have a setting where not only C is being given to the generator to improve ability to generate X prime, but we're actually making sure that X prime can trick this classifier here to give the right classification. I wouldn't say trick it, we just need to make sure that it does actually give the right classification from that point of view of that classifier. So this is basically different ways that we can GANs together. Another way to do this is to look into vector quantized VAE models. So vector quantized VAE models is the idea that the latent representation, rather than being a continuous value, can be represented by a quantized value. So if you have learned, for example, in the past about dictionary learning or any kind of quantization methods when you're trying to find a categorical representation of the data, this is exactly what's happening here in vector quantized models. So the latent representation Z is a vector with a series of values, right? And the interesting thing is when you have a series of values, let's say you have a series of values here which are a continuous series of numbers, so each one of these points is a latent representation of your autoencoder, for example. What you can do is you can place a series of points in this space. For example, this point here in green, and maybe you have another point there in green and another point there in green. And they can be indexed. For example, this one here might be the index 1, and the other one there might be index 2, the other one there might be index 3. So if these centroids in green are in the right position, then you can basically say, for example, this pixel here, this specific sample here, which has these coordinates, can be replaced by this index there in green. And by replacing the index, what we are doing is we're approximating the location of that point by a point which is quantized. It's just a subset of points. So these points are called atoms, or are called dictionaries, and they're optimized with the algorithm. So every time we do a forward pass, we end up with a series of feature representations that come out of the encoder. These features representations go through a quantization process where they are mapped to a series of atom elements that are spread around the space of the latent representation. And then we take those quantized methods, we dequantize them, so we map them back into their coordinates. And after mapping them back to their coordinates, we can now pass them to the decoder and reconstruct. So why do we want to do this approximation? The reason we want to do this approximation is because the quantization process is much more memory preserving. So if we can represent a very complex feature space, like a high dimensional feature space, by only, let's say, 32 atoms, we are going from, let's say, initially you have a floating point 32 vector of, let's say, 32 elements. And in that setting, you're going to have 32 by 32 bits of information. If you now are in another setting where you only have 32 atoms, you now only have 32 different variations of what that output might be. And for 32 variations, for 32 element variations, we're basically talking about 5 bits of information, because obviously 2 to the power of 5 is equal to 32. So we went from a situation where the original vector had 32 by 32 bits of information into a situation where we have only 5 bits of information. So we have significantly reduced the size of the encoding space. And the reason why we want to have small sizes in the encoding space is because obviously it creates a more compact distribution. So if each one of the elements of that code space, of that latent space, is a quantized vector, we now have a sequence, or we have a series of quantized vectors that represent an image. So if you take an image here, for example, you pass it through an encoder, and you end up with the representation here, which is a spatial latent representation. So it has a spatial component, and each one of the spatial elements is then converted into a series of categorical values corresponding to the index of the atom elements. So this image here, for example, that element there has an index of 1, index of 3, index of 2, index of 53. So this image here shows that at different locations you have different indices. You now have a sequence of pixels, or of voxels if it was in 3D, which are basically just a series of categoricals, a series of indices. And the interesting thing about series of categorical numbers is exactly what you normally do when you're looking into, for example, sequence models or recurrent neural networks and things like this. For example, like the ones that are used in natural language processing. We're going to learn about these in a couple of lectures, but there is a very interesting way for you to model sequences of numbers, which means when you want to generate a new image of this sort, you can then just generate a series of integer numbers as a sequence by training a model, in this case, for example, a pixel CNN or a transformer model, to be able to learn how to generate those sequences. So VQVAEs allow you to transform a continuous representation into a quantized representation, which is much more compact. And the quantized representation can then be sampled from using sampling algorithms like pixel CNNs and transformers, which we're going to learn about in a few lectures' time. And that is then able to generate really high quality images. So these samples that you see down here are realistic samples of a VQVAE of people's faces. And it doesn't use anything very fancy from the point of view of GANs or any kind of advanced training methodologies. It's just having a very large latent space, which is actually made small via the quantization process. And if you were to generate these vector quantized samples from the model at different degrees of resolution, if you only have the top encoding space, which is the lowest resolution one, the image is going to be a poor resolution. But when you add the next band up, so the middle representation and the bottom representation, so the highest resolution one, you end up with images that have really, really high fidelity, including all of the little hair wisps that you can see here when you compare it to the original data. So vector quantized VEs have a compact representation, which produces reconstructions which are very high fidelity, which is one of the reasons that they're now being explored in a medical imaging setting, because they're actually quite memory preserving. Vector quantized VEs have been used in many, many different scenarios. For example, one of the nicest implementations that I've seen is the jukebox paper, where they were using VQVEs as ways to generate new musics and new sounds. So not only you can look at the encoding space, and you can then project the encoding space to a lower dimensional space and see that different genres of music are encoded in different parts of these sound or music wave distribution. What you can also do is, by sampling from the model, you can generate new songs. So the sequence models that represent the sound wave again are quantized using the vector quantization processes, and they become a sequence of quantized vectors. And the sequences of quantized vectors can then be modeled using something like a transformer or a RCNN or any kind of token-based sequence model. And if you then sample from the model, you can generate new images. And if you look at the demos that exist for Jukebox, you can actually generate really interesting music, which does not really extrapolate much from what has been trained on, but you can generate really interesting chimeras, change styles, and generate music that I would myself consider to be quite pleasant. So I think it will be a really interesting way to think about music in the future, because music, similarly to images, is still a compositional process. It's a process where a human decides which notes to play in which order, and that's part of the creative process. But there's also quite a lot of patterns that exist that come from the way that music is built, and these patterns can be learned by algorithms, and new music can be generated. Maybe this music doesn't have the same passion as some other music does, at least at the moment. It might not, but it does create a very interesting point of discussion as to when does creativity stop and when does algorithms and logic start from the point of view of creating new music or new art in general. You can always add a discriminator to a vector quantized model, obviously. So if you have a VQV model, which is trained purely to be able to reconstruct images, you can further enhance its capabilities by adding a discriminator at the end of the image. So when we generate an image, you can basically take the generated image and put it through a discriminator and make sure that the discriminator is predicting that the image is indeed true or false. The other thing that you can do is, depending on the resolution of the discriminator, you can make the discriminator work in patches. So you can feed different patches of the discriminator to different patches of the generated image to the discriminator to make sure that the image is found to be real in all of the different areas, which means the discriminator cannot, for example, focus on one specific region to make sure that that specific region is the one that is triggering the true or false detection. It needs to be made true or real, or it needs to confuse the discriminator in every single part of the image, meaning that it enhances the clarity on all parts of the image rather than only enhancing the clarity in the part of the image that has initially tricked the discriminator. Okay, excellent. I hope you enjoyed the lecture, and I really do hope that by the end of this lecture you now understand the differences between autoencoders and variational autoencoders, which is what we saw in the previous lecture, the influence of the KL divergence on the code of the vector of the variational autoencoder and its applications, and ways for you to factorize and make sure that what is represented in this late representation is actually decoupled and factorized. Hopefully you also understand now a little bit better what are generative adversarial networks, the fact that there is a generator which is receiving random samples and generating images that can then be fed into the discriminator that make sure that those images are either real or fake. You also understand the limitations of GANs, and we don't see them as a panacea. GANs have an immense potential, and they're a very hot topic for research, but they're also something that is very hard to stabilize and something that is more of an art than a science. It's very hard, and you really need to get the feeling on how to appropriately train GANs before you get some proper results out of them. You also saw a little bit of the improvements that have been made in GANs to make sure that they are becoming more and more stable, and we finalize by looking into different variations of GANs and VAEs and GAN VAEs, by looking at all these different complex models that try to bring the best of both worlds and combine different technologies in a single model. So with this in mind, I'm just going to give you here a few resources that you might want to read, a few papers about GANs, VAEs, and BTVAEs. These are all quite classic and very good quality papers. I probably wouldn't read all of them, but I would definitely motivate you to read some of the older ones that have proposed, the ones up until maybe 2018 and 19. Those ones are really strong papers that have proposed a series of methodologies that are going to be very influential in the very near future. There's also here a few more resources regarding the VQV model and also autoregressive models, which we really didn't have the time to discuss here today. Thank you very much for listening to today's lecture. If you have any questions, do send me an email or ask via Moodle. I'll be more than happy to answer your questions. Otherwise, we can also ask me during the tutorial session that we're going to have this Thursday.